Now let's look at question number 3 in the project. It's a question on chapter 10, comparing two means. So the question is about driving distances, data on household vehicle miles of travel, VMT, are compiled annually. Independent random samples of 15 Midwestern households and 14 Southern households provided the following data on last year's VMT, vehicle miles of travel, in thousands of miles. So even though they've given us the data here, we have also summarized for you the data. So the sample mean for Midwest is 16.20.23. For S sub 1, that is the sample standard deviation, is 4.06. And then the sample mean from South, from the second population, is 16.23, and S sub 2. Now S sub 2 and X sub 1 are exactly the same. So I'm going to change that to 4.42. I'll have to check what I have there in the project I posted on Canvas. I may have already changed it there. If not, I will update that. But if you have worked on it or and you see that the sample standard deviations are the same, then please change S sub 2 to 4.42. All right, it shouldn't matter because this is just for practice. All right, so we have summarized the data for the sample mean 1, 16.23, S sub 1, 4.06, N sub 1 is 15. And for the South, it's X bar sub 2 is 17.69, S sub 2 is 4.42, and N sub 2 is 14. All right, this is the sample size for the second population. So the question is, at the 5% significance level, does there appear to be a difference in last year's mean VMT for Midwestern and Southern households? So we are performing the hypothesis test at a 5% significance level, which makes alpha equal 0.05. And it says, is there a difference between the two means that makes it a two-tailed t-test? All right, so it's going to be a t-test. Again, keep in mind that for all chapter 10 questions, we are using the t-distribution. All right, you don't have to look for whether the sigma is provided, the standard population standard deviation is there or not. Doesn't matter. All right, we are using the t-distribution for all questions on chapter 10 whenever we are comparing differences. So the first part says state hypothesis, which is null hypothesis, colon, H sub 0, colon, mu sub 1 equals mu sub 2. Please don't put a value here for mu sub 2. It's just going to be stated completely in variables. So mu sub 1 equals mu sub 2. We are comparing the two means. So the null hypothesis will say that they are equal. All right, a null hypothesis always has an equal sign. Again, always stated in terms of the population. Alternate hypothesis is going to be mu sub 1 not equal to mu sub 2 because it's stating that it's not same, they are different. All right. Then number 2 is to state the significance level. Alpha is 0.05, but because it's a two-tailed test, it's going to be split into 2. So alpha divided by 2 is 0.025. Okay, and then once we have our alpha by 2 and we know it's going to be a t-test, you can go ahead and find your critical value. So plus minus t of 0.025. Now, what is the df here? The df equals 27. So what is the formula for df in a pooled test? All right, is df equals n sub 1 plus n sub 2 minus 2. That should also be there in the formula sheet. All right, this is a pooled test that we are using because the standard deviations are very close. All right. If you do S sub 2 divided by S sub 1, remember that rule I spoke about in the lecture and also in the worksheet solutions. To decide whether we can use the pool test or not, just take the higher standard deviation value divided by the smaller standard deviation value. If it is less than 2, then you can safely go ahead and use the pool test. All right, the pool test is somewhat simpler than the non-pool test because the degrees of freedom has a much simpler formula, all right, in a pool test. So we use the formula, which is n1 plus n2 minus 2 equals 15 plus 14 minus 2, and that's how we got 27 for our DF. So when we find our critical value, we have to look for a DF of 27. So number 3, part 3 is always, or step 3 is to compute the test statistic, and this is a pooled test. It says S is pooled as S sub 1 and S sub 2 are almost equal, and you see I've taken the ratio of the higher over the lower, the ratio of the higher and lower standard deviations, and it gives a value 1.09, which is well under 2. It's almost, it's closer to 1, way closer to 1. So we have to first find S sub P. We have to pool our standard deviations, and S sub P goes with this formula here. All right. It's n sub 1 minus 1 times S sub 1 squared plus n sub 2 minus 1 times S sub 2 squared divided by the DF, and then you take the square root. So make sure you plug in all the values correctly, otherwise you'll end up with the wrong S sub P value, which is going to affect your T sub 0 value, all right, eventually. So again, here are the calculations. We come up with the S sub P value of 4.237. And once we have our pooled standard deviation, plug it into this equation. Where's the equation? Here is our equation for, all right. Here is the equation for our test statistic. All right, plug in the X bar values and we come up with a T sub 0 value of negative 0.9275. Now, another thing I want to state for the test, unless the question says otherwise, always keep your decimals to the third decimal place. All right, so more the better. So here I have negative 0.9275. You could have written it as negative 0.928. That would be all right, but do not make it negative 0.93. All right, that's going to be rounding it up too soon. Okay, so please, by default, unless the question states otherwise, please use 3 decimal places in your values, calculated values. All right. So here's our T sub 0 value. We use the critical value approach here. First find the critical values. They'll be on both sides. It'll be plus minus. If it's a two-tailed test, make sure you write your critical values as plus minus. And then bring your test statistic, which is negative 0.9275. See where it falls. It's going to fall somewhere, negative 0.9275. It's going to fall somewhere here. It doesn't show it, but it's going to be, let's just put it here. Definitely in the do not reject region, right? Negative 0.9275. Please show it on the diagram. And also write here that it falls somewhere between the two critical values, which is the do not reject region. So the decision is going to be do not reject. And then for the p-value approach, we have a p-value of 0.1809. Just multiply that by 2 because it's a two-tailed test, and only then compare by with alpha. All right. So it has to be either 2 times 0.1809 compared with alpha, or you can just find the p-value on one side and compare with alpha by 2 like we've done here in this case. All right. So in any case, 0.1809 is not less than 0.025. So we do not reject null hypothesis. 0.18 is way larger than 0.025. So the decision is do not reject null hypothesis. Interpretation at the 5% significance level, always again start with that. There is not sufficient evidence to conclude that there is a difference in last year's mean VMT, again stated in context of the problem. And you can always copy that verbiage straight from the question. It says here, does there appear to be a difference in last year's mean VMT? So you're saying that there's not sufficient evidence to conclude that there's a difference in last year's mean VMT. Just copy the verbiage. You don't have to scratch your heads and think, what wording should I use? All right. Okay. All right. So the next part says find the confidence interval. We are using a 95% confidence interval. So again, like any confidence interval question, it's very formulaic. It's the same steps. All right. You're just using a different formula, and formula will be given to you. So it shouldn't be that difficult if you know the steps. All right. It's very quite mechanical by now. Now, confidence interval we are using is 95%. Confidence level is 0.95, which is the decimal version of the confidence interval. Alpha is 0.05, alpha by 2 is 0.025. For confidence interval, you always have to split your alpha into 2 because the confidence intervals stretch on both sides of the center point. DF 27 obtained from that same formula, n sub 1 plus n sub 2 minus 2. All right, so that's how we come up with 27. Find your t of alpha by 2 divided, t of alpha by 2 with df. We should actually write with df of 27. And then this is the formula to use for confidence interval. It's x bar 1 minus x bar 2 plus minus t of alpha by 2, and then s sub p, which is the pooled standard deviation we found earlier, times square root over 1 divided by n1 plus 1 divided by n2. So here I've plugged in all the values. Make sure you plug in the values correctly and make sure it's t of alpha by 2 multiplied, and because sometimes I have students forgetting that, it's t of alpha by 2 multiplied by s sub p. That's why I have two values and then the radical. Okay, so once we complete the calculation, again, always calculate your error, margin of error first, and then add and subtract with the subtract from the difference. So these are the end points, all right, of our confidence interval, 95% confidence interval. And we see that one end of the confidence interval is a negative, the other one is a positive. Now these are valued, these are differences, all right. It's x bar sub 1 minus x bar sub 2. That means it's the difference between the two sample means, all right. So it contains a difference of 0, right? This interval contains a difference of 0, which means when the difference is 0, when the difference between two numbers is 0, that means there's no difference in the values. The values are the same. That's what it means, correct? So we got based on this confidence interval, or the signs of the endpoints, we see this matches with our decision of do not reject the null hypothesis. The null hypothesis was stating that the two means are equal, and the confidence interval results kind of confirm that. All right, it contains a difference of 0. That means this confidence interval is saying that there's no difference, which matches with what our decision we came up with from our hypothesis test. Again, for the confidence interval also, you need to interpret. We are 95% confident. So this time it's not at the 5% significance level or at the 95%. There's no 95% significance level for confidence interval. It's 95% confident. That's the word you have to use. But the difference, again, this is a key word in chapter 10. When you're interpreting confidence interval, you have to say the difference between last year's mean VMTs by Midwestern and South households, or for Midwestern and Southern households, lie in the interval between these two endpoints. Since the interval contains a zero, there's no difference in the means. That's the conclusion, right? So that's question number 3 from chapter 10. Now here's question number 6, which is a practice on non-pool t-tests. All right. So it says, provided below are summary statistics for independent simple random samples from 2 populations. Use the non-pool t-test and the non-pool t-interval procedure to conduct the required hypothesis test and obtain the specified confidence interval. So again, this is not an application-based problem. They've given us the summarized data here for both populations, summarized sample data from both populations, and they've said perform a right tail test with alpha equals 0.05, the significance level. Okay, so right tail test means the alternate hypothesis is going to say it's greater than the mu sub 1 is greater than mu sub 2. All right, so that's how you're going to decide what sign will be between the two means. All right, greater than because it's a right tail test. All right, the null hypothesis will always state that they are equal, so no doubts about that. State the significance level, it's 0.05, and then it says draw a diagram showing rejection and non-rejection regions. So because this is a right tail test, the reject region is only going to be on the right hand side. The left side is going to be do not reject, but the area corresponding to the reject region under the curve is going to be 0.05, which is the value of alpha. Alpha represents the probability of rejecting a true null hypothesis, right? So that's why it's always the area of the reject region. So the critical value is going to be T of 0.05 with DF of 28. Now, T of 0.05 here, we do not need to split alpha. This is a one-tail test. So please don't use alpha by 2. It's just alpha. Okay. So if you use your table, you should come up with a value for the critical value. All right. This is going to be the critical value is going to be 1.717. This value here is going to be 1.717. So now we calculate our test statistic. This is the formula for the pooled, this is the formula for the non-pool test. We are using the non-pool test. So make sure that you pick the right formula from your formula sheet if it's not given to you. If it's given to you, then use whatever formula is given on the test. But if it's not given to you, you have to look it up from the formula sheet, which will be provided to you. You do not need to memorize any of these formulas. All right, but make sure you pick the right formula for non-pool test. So you use this formula and find your T sub 0 value, which comes to 1.107. Make sure you are plugging in the values correctly. All right, now, next step, we have to find the DF. Now, if you recall from our lectures and from the worksheet solutions, we said that the DF for non-pool test is rather complicated and it may be difficult for you to work on the test. So what I'm going to do is I'm going to give you the DF value. All right, so please work through this entire problem using the given DF value, whatever is given. And then after you complete the entire test, if you have some time, you can just work out the calculation as a verification of the given delta value. Now, because this is something that you're working on your own as a practice, it's not a test situation. I have not given you the delta value. However, be assured that on the test for this non-pool test, you will be provided the DF value. What I'm trying to say is, do not waste time on the test calculating this cumbersome equation. All right. The DF, anyway, the calculation comes to 22. So that's going to be the DF we are going to use. And then we go to our critical value and we find our critical value DF equals 22. And we see that our test statistic was 1.107. It was less than 1.717, which is our critical value, and it falls in the do not reject region. All right, so the decision should be do not reject. And again, here is the working of the p-value approach. Again, by now you should be pretty familiar as to what the steps are for the p-value. You find the area corresponding to your test statistic value with DF of 22, which is this value here, and I use my calculator to come up with this value. Okay, this is this is an exact value for the p-value. If you're using your formula sheet, then it's going to be an estimated value. All right, and then you compare with alpha. If it is less than alpha, then you reject. If it is greater than alpha, then you do not reject. All right, so that's the p-value approach. And then you write your decision and then you interpret it. Again, because this is not an application-based problem, you cannot state it in context of the problem, so you're going to use your alternate hypothesis statement in your interpretation. One thing I want to correct myself here. Somewhere I think I saw that we were using a DF of 28. This is incorrect. All right, this should be 22. Let me just... Actually, it was not possible to do this calculation until we did our calculation for the of the DF, this, and I think when I wrote this solution sheet, I'm sure I first calculated my DF and then came back here to find the CV. All right. So here is the solution for the confidence interval. We are using a 90% confidence interval this time. All right. So you have to split your alpha into 2, 0.05. DF is already calculated. Again, on the test, it will be given to you. So please use the DF value given to you. And then this is the formula to find the confidence interval in a non-pool test. And just do the calculations and then finally interpret it correctly. All right, again, note that the endpoints of our calculation of the confidence interval, the endpoints have opposite signs. Left-hand side has a negative difference. The right-hand side has a positive difference. It contains a difference of 0. Therefore, there's no difference between the two means, and that's what the hypothesis test also said. We came to the conclusion that we are not rejecting the null hypothesis, right? Now this, I believe, is the last question from chapter 10. This is on paired populations, all right, where there is a special relationship between the two samples, all right, and they appear as pairs. So this problem is about Gosset. In one study, used the following data set, which gives the additional sleep in hours obtained by 10 patients who used a certain drug. So most likely what happened was a new drug, some pharmaceutical company or a medical community probably came up with a certain sleep-inducing drug, all right, and it was applied on 10 patients, and they took the measurements. They measured their sleep hours before administering the drug and then after administering the drug. And these numbers here represent the difference in the sleeping hours. So in one case, 1.9 hours of more sleep the person got after administering a certain drug. In another patient, it was he slept 0.8 hours, 1.1 hours. Now this is a case minus 0.1. He slept a little bit less than before the drug was administered. So these represent differences. All right, these represent differences in the sleeping hours. So you don't have to find the difference in the pairs. This is summarized data, right? This table represents the difference, the additional sleep in hours, which means the difference in before and after, the difference between before and after. So the questions are: identify the variable under consideration. What are we looking at? Hours of sleep. Identify the two populations: hours of sleep with drug, population 1, and hours of sleep without drug, which was population 2. Identify the paired difference variable. The paired difference variable is the additional hours of sleep obtained by each person after using the drug over hours of sleep not using the drug. Are the numbers in the table paired difference? Why or why not? Yes, they represent the difference in paired value for each of the 10 patients because we took the hours before and after for the same patient, so it's paired. E says at the 5% significance level, do the data provide sufficient evidence to conclude that the given drug is effective in increasing sleep? So again, the key word here is increasing, which is going to be used to state our alternate hypothesis. Now, what else have they given us? The mean difference, D bar, anything with a bar in it in statistics means mean. So mean difference is 2.33 hours and the standard deviation of the difference is 2.002 hours. All right, so they've given us this information, which is going to be very helpful, which is going to save us a lot of calculations. Let's go on to working the problem. Step 1, always state your null and alternate hypothesis. Null hypothesis is going to say the mu sub 1 equals mu sub 2, and alternate is going to say mu sub 1 greater than mu sub 2. Why greater than? Because in the question it says here, up here it says, do the data provide sufficient evidence to conclude that the given drug is effective in increasing sleep? So that's why whether mu sub 1 is greater than mu sub 2. All right, so right tail test, all right. We sketch our region, reject region is to the right, and a right tail test, then do not reject region, and the area associated with the reject region is 0.05. Determine the significance level. Alpha is 0.05. Calculate the test statistic. T equals, this is the formula, all right? If D bar and S sub D is given to you, then it's a pretty simple formula. Just plug in the value of D bar from here, and then S sub D also is given to us, divided by square root over, again, this is division, all right? Even though they appear next to each other, please don't end up multiplying the two. It's S sub D divided by square root over n. This is the answer I got for my test statistic. T sub 0 equals 3.68, all right? So 3.68, now we come and do our two approaches. What is CV? CV is T of 0.05 with DF equals N. Right now, for paired populations, the formula for the DF equals N minus 1. All right, N minus 1 is the formula, and therefore we have DF equals 9. All right, and then we come with our evidence, which is the test statistic. We see it's greater than 1.833. It falls in reject region. Therefore, we reject the null hypothesis, right? And then this is the p-value approach. Using the p-value approach, decision is to reject the null hypothesis. Both approaches give us the same conclusion, the same decision. So the interpretation is at the 5% significance level, there is sufficient evidence to conclude that the given drug is effective in increasing sleep. All right. And then for the confidence interval, 90% is the confidence interval we are being asked to find. You have to split your alpha into 2. So alpha by 2 is 0.05. The T of 0.05, T of alpha by 2 with DF equals 9 equals 1.833, which we use in our calculations. So here's the formula for the confidence interval. We add the margin of error to D bar. All right. So 2.33 plus minus 1.833 is from here. And then S sub D divided by square root over N. And when we do the calculations, we get a confidence interval from 1.17 to 3.49 hours. So both ends have the same sign, all right, positive. That tells us that mu1 is greater than mu2. And that agrees with our decision from the null hypothesis test as well. All right, so interpretation, again, this is a confidence interval interpretation. We are going to say we are 90% confident that the mean hours of sleep increase is between, sleep increase, I'll put a hyphen between the two, is between 1.17 to 3.49 hours. Let's make it more precise, before taking the drug and after taking the drug. All right. Now, I just want to go back and check on one other thing, all right? Okay. I just wanted to check one thing, how we had defined the two populations. The population 1 was hours of sleep with the drug, and then population 2 was defined as hours of sleep without the drug, all right? So that makes our alternate hypothesis statement valid. So mu1 was after taking the drug, and mu2 was before taking the drug. All right. So I just wanted to make sure that the alternate hypothesis was stated correctly based on how we had defined the two populations. All right. So these are all the questions pertaining to chapters 9 and 10 in this project. We also have chapter 12, which I'm also going to give you the solutions for, video solutions for that.